All right, so I've talked about at least the practical application of what we're going to learn today, which is with static code analyzers. So the idea of this theory is we want to come up with a way to allow a program to at least do some type of static code analysis of your program to report something back meaningful. You know, do you have buffer overflow? That's probably going to happen here. Maybe detect some other security violations, or maybe you have some dead code. And to do this, it needs to, we've talked about control flow graph. Hopefully you can see that can provide at least some information, but we also need to know about data flow. How is data moving around that's going to be used, especially if you want to do some type of buffer overflow, or another common example is SQL injection. You want to be able to trace when something from the user is going to be put into an SQL statement and make sure somewhere in that path someone did scrub it to make sure no one's injecting any SQL statements. So Chapter 5 talked about control flow, call graph, finite state machines. This time we're going to do about data dependencies. So where did this value of x come from? What's actually affected by a change of its value if it does change? And this has a lot of practical applications. One example, like I said earlier, SQL injection. You want to make sure that your code is actually scrubbing SQL, so you need to find the flow of code to ensure that you are scrubbing at some point. All right. Learning objectives are we need data flow, doing analysis, and basic trade-offs is what we're going to be going over today. So first thing, we'll get right down into it, is we need to come up with this idea of definition use pair, or def use pair. The idea is that the variable is defined somewhere, maybe declaration, initialization, assignment, maybe it's received as a parameter to the function, and then you need to find out where is it used. Maybe it's in some expression, control statement, parameter passing, or even in the return. Here's a great example, and I think this will help clear it up. Notice you have x defined here, and then used down here. Of course, we're assuming x is not defined or in here somewhere. So, one definition use pair for x from x here is that notice the use of x down here might be defined in this statement or might be defined somewhere else up the chain. So there's actually two ways x can be defined when entering this control. Again, SQL injection, make sure that it's been scrubbed in here, or maybe it's been scrubbed up here as well. Definition use pair. So here's a full GCD algorithm. This is the iterative GCD. And we're going to be looking at this example to drive a lot of the other explanations. So let's go ahead and take a moment to figure out what's going on. So public class GCD looks like Java. Int GCD passing into x and y. So notice that x and y are defined up here as well as temp on this line. So we have x up here, definition of x, y, and temp because it's in this block right here. Notice we're looking at data flow, so we combine all those statements. B is where we use y. So one quick definition use is from A to B for y. And then C, you have a temporary is actually being defined, is being redefined, and it's using x and y. So you're defining temp and you're using x and y here. D, you define x here, use y, x and y. Of course here you define y and use temp. And then afterwards you probably would jump up to the top. So notice here where it uses y could be coming from the function, or y could be coming from inside this loop, namely right here from E. So E to B is one definition use as well as A to B. And then if you return, you might be returning x where it's using x, but notice that what's kind of hard to see is while x is always coming from this B block, x might be defined from A or it might be defined from D. A definition clear path along the control flow graph from a definition to the use without another definition. So instead, nothing's killing the example. All right, saying there's oversimplification, we'll get to that in a moment. We're just trying to make this clear so you understand. So A, define x here, and then B is going to kill the old value. So then you have y here. So what's happening is while it's using x here, it's being defined at B. There's no clear path from A to C. It's not definition clear. But from B to C, it is definition clear because there's no other changes between these values. Hopefully you can see that this is actually what we want or what we're looking at, because if you're overriding x altogether, then it's a definition clear. Note that the caveat here is that you may have x equal to something something with x in it again, which kind of implies a little bit, but it's still the clear path is from B to C. All right, direct, all is in the control flow graph, edges, def use, pairs, labeled variables. So we're going to look at this graph a little differently now. Now, you probably haven't seen the code, so I went ahead and put it over here so we can at least reference it quickly. So what's happening? Your each nodes are your different codes. So notice you have your GCD, which can go into B of your while loop. Notice Y can go into B, and all that's saying is that if you have B here, the definition may come directly from A, or it may come directly from E. So if we go back here, B might come from A, or B might come from E. Okay? And then, well, B actually is the end of this whole block, and then later on we could return. Because if you look at F, which is at this very end, where is it using F? Well, it could be pretty much from A, or is coming from D. F coming from A, or it's coming from D. The B part is actually superfluous. Yes, we know it's coming through it, but really the only definition used, clear, direct definition used is between these two. And then internally, C, which is that temp, aka what's come after the while loop. It could come from, well, A and Y definitely are going to come from A, or notice that Y could also come from D, Y could come from D, sorry. X could come from D, Y could come from E. That is a typo. That should be an X. Temp, which is defined right here, is always from E is going to come here, and notice that D is going to have two possibilities coming up. Notice that this flow graph is a little different because it's kind of jumbled around a bit about what the control flow would be, but that's because we're looking at the data dependencies of each variable. This didn't make too much sense. Please pause it and at least look at this slide and the code next to it. Hopefully online you can basically swivel from one screen to another. All right, where are these? So beforehand, direct graph with all of the data used. Now we really just want to know, okay, look, where can these values come from? And this is probably the most useful piece of information where we can distill it all down. So again, nodes is control flow graph, edges unlabeled from entry to exit. So A, any value that's defined here might be used in B or F. But before it can get to C, where temp is declared, it has to go from B and go through A, which is probably what we're used to, and then E, which also is inside of the loop. That Y may come from B, and then D, which uses X. Well, X is coming, which is Y. X, sorry, coming from while, aka up from the A. Nice. Okay, dominators. All they're using or trying to talk about here is that node M dominates N if every path from the root passes through it. So you may have something that dominates every other thing, aka it kills it all. I think the picture really helps describe what's going on here. A predominates all nodes because all these other nodes have to go through A first. F and G are post-dominant. F and G post-dominate E. So F and G post-dominate E. Okay, once you hit E, you have to go through F and G. So it's post-dominant. G is the intermediate post-dominator of B. Notice it says immediate post-dominator. That means once you're at B, you have to the next block of code you have to execute would be G. Now you could have gone through CD or you could have gone through EF, either one of those, because you're not required to specifically do one or the other. But I mean, naturally you'll have to do one. But the point is, which piece of code do you have to? And of course, C does not post-dominate B because you could go along with E. And B is the immediate predominator of G because it's the first thing before G that you have to execute. Okay, control dependence. Give a more precise definition. All right, sure. Consider node N that's reached at some point but not executed. There's some code C in the following property. Basically, to successor control graph C is not put to. All right. This is just the more precise way of explaining what we just did earlier. If you need it, which you probably will be you will need to go through this for your homework. So keep in mind that C has if you're saying there must be some code C with the following property, has at least two successors. C is not post-dominated if there's successor. Wow, C in the control flow graph that is post-dominated by N. When these conditions are true, we say N is the control dependent on no C. So it's actually control-wise what is on C. Again, picture's going to take it a little better. Execution of F is not inevitable at B, is all we're saying, because it could take this other route. Execution of F is inevitable at E, so F is control dependent on B, because it's the last point at which control execution is not inevitable. So we're trying to say control dependent, because we're saying that at B is when it's finally decided whether F is going to be executed or not. All right, I'm going to stop here. We'll go ahead and do the next presentation on the rest of this chapter.